Okay, so here's what we talked about last time. We talked about, just quick review, some important stuff. Remember, we said that relative extrema occur only at critical numbers, right? There's two types of critical numbers. Relative extrema meaning peaks and valleys, right? Relative maxima would be peaks, relative minima would be valleys, okay? So there are two different types of critical numbers. One of them is where the derivative is equal to 0, right? That's where we would have horizontal tangent lines, and we would have potentially extrema of the smooth type, the rounded type, so rounded peaks and rounded valleys, right? The other kind would be places where the derivative is undefined, and that would give us sharp peaks and sharp valleys, okay? But this is an important thing to remember. Not all critical numbers produce extrema. Sometimes we'll have false alarms. You can have places where functions, like look at the green function here, you can have places where functions have horizontal tangents that are not extrema, right? In this case, it's a point of inflection. You can have places where functions have undefined derivatives that are also not extrema. So we've got to check all of the critical numbers to figure out which ones produce extrema and which ones don't. We do know, though, that all relative extrema necessarily occur at critical numbers. So our list of critical numbers we're going to build will always include all of the possible extrema, okay? But some of them may be false alarms. And so then the goal for today, in quick vocabulary summary, relative extrema are peaks and valleys, right? Relative maxima and relative minima. Absolute extrema refers to the maximum value or values and or minimum value or values. So the highest and the lowest points on a specific interval. And global extrema refers to the maximum or minimum possible values the function could ever have on its biggest possible domain, its natural domain, okay? The bottom one isn't probably as important as the top two. The top two, items 1 and 2, are really important. That stuff we'll talk about today. Okay, so let's start off here. Just a quick, just kind of a recap, a little warm up from last time. Let's use this graph here to identify some specific points. So there's a graph of a function that has closed endpoints. So I want to know, where are the local minimum points? So the local minima occur at what x values? We'll just go down the line here. Andy, give me one value where there's a local minimum. Same thing as local means relative. Local and relative are interchangeable. Remember, local or relative minima are valleys. Local or relative maxima are just peaks. Are you talking, Andy? Can you guys hear him? Oh man. Okay. Hang on. I gotta quit and come back into this. I can't hear you. Okay, one more time, Andy. Give me one place where there's a local or relative minimum. Whoops. One more time, Andy. Give me a place where there's a relative minimum or a local minimum. Can you guys hear Andy? Oh my gosh. Okay, type it in chat. I can't hear. I don't know what's going on with my dumb computer. Somebody else say something. Kyle, say something. No, I can't hear you either. Okay, so yeah, Q is a place. Good. Okay, give me another place. Andrew, another place where there's a local minimum. Type it in chat. There you go. Here, let me try this one more time. This is driving me nuts. Okay, somebody say something. Nope, nothing. Jeez. I don't know. All right. So then, so any other places? Thumbs up, thumbs down, everybody. Any other places where there's local minima? Nope. Okay. Where do relative or local maxima occur? Oops, never mind. There we go. Okay, so relative maxima occur where? I'll just read lips. Okay, Kyle, you said P and R, and you're correct. Okay, and those are the only ones. Okay. No, I don't think so. I don't think so. It just does this sometimes. Our technology seems to just be not so great. Absolute minimum. Where is the absolute minimum in this case? Absolute minimum. Madeline, just go ahead and type it in chat. Looking for an absolute minimum. Anybody, just type it in chat. There you go. S. I don't agree with that. I think there's a lower point. A, there we go. A, good. The endpoint is lower than the relative minimum at S. Everybody agree? Okay. In this case, where is, and you got to look pretty closely here, I guess, where is the absolute maximum? I agree. I think it's P. P looks like the highest point. Okay. All right. So let's try. This is going to be really awkward if I can't hear you guys, but we'll do our best. So we're going to start off. We're going to look at some problems where we're trying to identify the absolute extrema on an interval, okay, on some interval. What are the steps we follow to do that? So here's our guidelines for finding absolute extrema on a closed interval where the endpoints are included, okay? So think about this logically. What are the only possible places where absolute extrema could occur? Like if we were to look back at this last picture, what are the only possible candidates for the absolute minimum? Wouldn't they just be the relative minima, the valleys, right? The locations of the valleys, or the endpoints? In this case, the endpoint ended up being the lowest point, the absolute minimum. What about the absolute maximum? Well, then it would be any of the peaks, the relative maxima, or the endpoints. And in this case, one of the peaks was the highest, right? So when we're trying to find absolute extrema, all we really need to do is find all of the critical numbers in our interval, because we know for a fact that all relative extrema must occur at critical numbers, right? So we're going to locate all the critical numbers, find those. We're going to evaluate the function at each critical number, okay? And then we'll just evaluate the function at the endpoints. And the winner for the absolute maximum is going to be the biggest value of those places that we identified in steps 2 and 3. Whichever produces the greatest value, that constitutes the absolute maximum. Whichever one produces the smallest functional value, the least functional value, that's going to be the absolute minimum. So let's try this. let's try this on a problem. Here they give us a function, f of x equals this polynomial function, 3x cubed minus 3x squared minus 3x plus 2. And we're looking at this on the closed interval from -1 to 0. Okay, I'm about to give you one of the greatest mathematical gifts I could possibly give you. You're going to take this with you in college, and you are just going to make these other students, they're just going to be so jealous. You're going to become the most popular mathlete in your class. Because everyone's going to want to know how you did this so easily. Okay, this is my tabular method for sketching curves, and in this case, we're going to use a tabular method. We're going to build a table that's going to contain all of our work for finding absolute extrema, absolute maxima, and minima. And here's how we build these super cool tables that you're going to learn about. It goes like this. Okay, we're going to make the top row of our table acts as the x-axis. And then we're just going to make rows. As we work our way down, we're going to make some rows here. So the first row we're going to make is our input values. That's going to be x. The second row we're going to make are the output values, y, or we'll call it f, and either one, doesn't matter, y or f. This is f of x, right? And then we're going to make a third row, which is f prime. So our endpoints, we already know, are at -1 and 0. So we're going to include those in our table. We're going to put a closed bracket on the left side down here at an x value of -1. We'll put another closed bracket up here at 0. And then we just want to find, are there any interior critical numbers? By interior critical numbers, I'm referring to any critical numbers that fall within between the endpoints of our closed interval. So we're looking for, in other words, we're looking for critical numbers on the open interval from -1 to 0. Okay. So we're looking on this open interval. Well, how are we going to find our critical numbers here? What do we have to do to find critical numbers? You can't tell me, so I'm assuming that you're all telling me right now. I can hear it. I can read lips, and you're all telling me, well, we're going to take a derivative, right? Because we find the critical numbers via the derivative function, right? If we back up a couple slides, critical numbers, relative extrema occur only at critical numbers, right? They always occur at critical numbers, and there's two types of critical numbers, and both of them rely on the derivative. We want to know, where is the derivative equal to 0 or undefined, right? So we need to take a derivative here. So here's our function f of x. Let's calculate the derivative. It's an easy one to calculate this time. I'll just do it up here, how about? So what is f prime of x here? Well, you're all telling me right now we're going to get 9x squared minus 6x minus 3, right? There's our derivative function. And now we just want to know, okay, well, where is our derivative undefined and where is it equal to 0? Okay, because those are the two species of critical numbers that we're looking for. So, well, right away, we know that f prime is nowhere undefined. And that's how we'd say it in math. And we don't even have to say it's nowhere undefined on our interval because that's a polynomial. It's defined everywhere, isn't it? Our derivative is defined everywhere. So we're not going to get any critical numbers where a derivative is undefined, but where is it equal to 0? Okay, let's try that one. F prime equals 0 when 9x squared minus 6x minus 3 equals 0. There's our derivative function. Okay, here's where I would ask you to help me out with the algebra, and you would all tell me that we're going to factor this thing, right? Okay, so the first thing we always try to do when we're factoring quadratics is we want to see if we can factor out a greatest common factor, right? In this case, I could factor out a 3, couldn't I? So I undistribute a 3, and we're left with 3x squared minus 2x minus 1. But this is a constant factor. I can divide both sides of an equation by a constant factor, and that's fine to do. I don't lose any solutions. I can't divide both sides by a variable or I lose solutions, but I could divide each side through by 3 and just get rid of that. And actually, if I wanted to, in the previous step, I could have even just done this. I could have just divided each side by 3 to get to this result also, okay? So now I've got to factor this quadratic. Okay, how did you guys, well, I know how you did because I taught you. Remember, there's 2 ways you can do this. You can use the goofy trick called slip and slide or bottoms up, or I can't remember what it was called. And now we always talk about it as slip and slide, but I hate it because it's not algebraically rigorous. You skip some steps with it. And so you might remember back in Algebra 2, hopefully, of course you remember, that the preferred way for Mr. Oya, and now for you too, is that we're going to do this by grouping. Okay, if you factor by grouping, it's a rigorous process. The algebra steps are all consistent. You don't have to do any trickery here. Really the bottoms up method is, and I'll review it with you real quick here, but it's really not that good. So with grouping, remember how we do this when we're factoring an inconvenient quadratic, meaning one that doesn't have a equals 1. That's why we're doing this. Otherwise, we would just factor this easily, look for magic numbers and be done with it. But because a is equal to 3, we don't have that option, right? So when we're going to use grouping, we got to find our magic numbers. And they have to do 2 things. They have to multiply to a times c, and they have to add to b. So they're factors of AC, and they add to b. Well, they're going to be factors here. A times c is 3 times negative 1. So they have to be factors of negative 3 that add to negative 2. Do those magic numbers exist? You're telling me, yeah, they do. That would be negative 3 and positive 1, right? So my magic numbers are going to be negative 3 and positive 1. So then what we do is we're going to split b into the sum of our magic numbers. So we're always just going to split that middle term, right? So we end up here then with 3x squared minus 3x plus 1x minus 1. And it doesn't matter the order you put those in. It makes no difference. It's going to work either way. And now we factor by grouping. Okay, remember this stuff? We just split this thing down the middle. And remember what we do. We're going to factor the first group over here. We're going to break up into the greatest common factor, which would be 3x times the binomial factor that's left behind. If I undistribute a 3x, I'm just going to get an x minus 1. Okay, well, the other group, we know that we have to get the same binomial. These two have to be equal. So from group 2 over here, I'm going to have an x minus 1 times what? What do I have to factor out to get an x minus 1 left over? Well, I'm just factoring out a 1 in this case, right? So now I've got my 2 groups. I've got 3x times the quantity x minus 1 plus the quantity x minus 1, times 1. Then we're just going to factor out of each group our common binomial. And so this is equal to x minus 1 times whatever's left behind, right? Well, what's left behind here? I've got a 3x plus 1. And so now I've got it factored, right? So we end up with our derivative is equal to 0 when this product equals 0. So we get two results, either x equals 1 or x equals negative 1/3, right? Okay, did I make any mistakes? Type it in chat if I made any mistakes. Okay, guess not. And so we can put those values up here in our table, right? What were we doing here? We were just trying to find critical numbers. Okay, so we got critical numbers at 1, which is outside of our interval, right? So we don't care about that one, or negative 1/3. Well, negative 1/3 is, you want to try to make this somewhat relationally in the right positions because it's supposed to be an x-axis. When these get really busy, it helps if you put the negative 1/3 sort of where it's supposed to go on the number line. It's not that big a deal. Okay, what happened at negative 1/3? That's where our derivative equaled 0. So that's telling us that this was a critical number. Okay, now all we have to do to find the absolute extrema on our interval is just evaluate our function at both of the endpoints and our single interior critical number. So we're just going to plug those back into the function. Well, what do I get? If I plug negative 1 into my original function, I'm going to get negative 3 minus 3 plus 3 plus 2. So what is that, negative 1? I think that worked out to be. Okay, so I've got an ordered pair here at negative 1, negative 1. If I plug 0 in, I get 2. So I've got another ordered pair at 0, 2. And then if I plug negative 1/3 in, what am I going to get? So I'm going to get 1/9 minus 1/3, negative 1/9 minus 1/3 plus 1 plus 2. So what's that giving me? That's giving me, did I do that right? I'm assuming I did. I think I did. So that's going to give me 3 minus 4/9. So 23/9, is that right? Did I do that right? Somebody check me. Might be handy for someone to have Desmos pulled up here so you can just be plugging stuff in. Quick reminder why Desmos is so valuable for things like this. So I can define the function here, right? Okay, so f of negative 1 gave us negative 1. Okay. F of negative 1/3. Yeah, that's right. If I make that a fraction. Oh, 23/9. That's what I had. Yeah, never mind. 23/9. That's what I had. Okay, so then what's our winner here for the relative or for the absolute minimum? Well, the absolute minimum was right there, wasn't it? That was the smallest of my three candidates that produced the smallest output, the smallest Y value or value of F, right? So that wins as my absolute minimum. 23/9 is bigger than 2. So this critical number ends up being my absolute maximum. Okay, give me a 1 to 5 on that. Okay. So how much harder is this making it that you can't ask questions and things? Is it worth me like restarting my whole computer here? Yes or no? Or are we okay with this the way it is? If it is, you think so? Okay, we'll try it. But if I need to, we can pause things and I'll try restarting everything, and that probably will work. It just takes a little while, but I'm happy to do it. Questions are important. Okay, let's try another one. Find the absolute extrema, if they exist, as well as all values of x where they occur for the function. Okay, so in other words, we just want the values of x where the relative extrema occur. Okay, and if we actually wanted to, if this question had asked, which it did, what are the absolute maximum and minimum values? The absolute minimum value was the output. That would have been -1, and the absolute maximum would have been 23/9. Where they occur is at -1, x equals -1, and x equals -1/3, respectively. Okay? Let's try another one. So we're going to use our tables here. So I would recommend strongly that on a piece of paper, you're going through the table with me. I'll publish my notes as always, of course, so you'll have access to these. But just I think going through the table on your own will help you get used to the steps. So there's my x-axis. I'm going to be picking values at 0 is my left endpoint. 3 is my right endpoint. We're going to need a row for, we'll call it y this time, just to change things up a little bit. Here we'll call my next row is my output row, which we can call y, and then I need my first derivative row. Or for now, we just call it, well, actually, yeah, we know about first derivatives and second derivatives, so we just need a first derivative row. Okay? We've got to differentiate our function. So f of x is equal to 4 minus x over 3 plus x. So let's find the derivative here. I'm going to have to use a quotient rule, aren't I? Unless I were to rewrite this as a 3 plus x to the -1, then I could use chain rule and power rule. But we'll just use quotient rule. So f prime of x, I'm going to get low d high. So 3 plus x times the derivative of the top is -1 minus the top times the derivative of the bottom, which is 1, divided by the bottom squared. Okay, and when all the dust settles there, what do I get? I get -3 minus x minus 4 plus x. So that's going to give me -7 over the quantity 3 plus x squared. Correct? Type in chat if I made a mistake there. Okay, we're good. I'm getting some thumbs up there. Okay. So let's find our critical numbers then. We've got our first derivative. Let's find those critical numbers. So where is f prime undefined? You could probably just show me fingers here. Where is, you have to be a little creative. Where is the derivative undefined? Okay, good. I'm getting some -3s. All right, I like that. Some -3. That's where the denominator is 0, right? Undefined at x equals -3, where is it equal to 0? There's my derivative function. Where is that equal to 0? Where is a fraction equal to 0? Just use your fingers and kind of use some creative sign language here. Where is a fraction equal to 0? Okay, so it could be, in this case, I'm seeing, okay, that was good. So it could be where the bottom is at infinity, right? That's one way to do it. What else? The bottom would be at infinity, in this case, at either positive or negative infinity. Well, that's well outside of our closed interval, isn't it? Okay, and it never actually gets there. Just in general, would everybody agree a fraction equals 0 when the numerator is 0? Okay, there we go. See it in chat. So the numerator here is -7. It's never 0. So f prime is equal to 0 nowhere. So we get no critical numbers where the derivative is equal to 0. We get one potential critical number at x equals -3, but -3 is outside of our interval. So we get no interior critical numbers. That makes this a pretty easy problem, doesn't it? Then the only places we have to check the outputs are at the endpoints. And so if I plug 0 into my function, I'm going to get 4/3. And if I plug 3 into my function, I'm going to get 1/6. So at what x value is my absolute minimum? The lowest value of this function on our closed interval from 0 to 3 occurs at what x value? Good, I'm seeing some 3s. Okay. And the absolute maximum occurs at 0. Okay. So does that seem like, did we miss any? Is there a possibility there could have been some values in between, though, that were higher or lower than those? Could there be some values between 0 and 3 where the function goes above or below the endpoints? Give me thumbs up or thumbs down. Yes, meaning there are. Thumbs up means, yeah, there could be some points. Thumbs down meaning no. I don't know what thumbs sideways means there, Kyle. Thumbs down is the answer, because the only place where there could possibly be any values higher than 4/3 or lower than 1/6 would have to be at a peak or a valley, right? Are there any peaks or valleys? No, there cannot be, because there were no critical numbers between 0 and 3. Relative extrema, aka peaks and valleys, can only occur at critical numbers, and there were none. So there's no possibility of any interior values of x where the function was higher or lower than the endpoints in this case. Okay, so we know that this is our absolute max, and this is our absolute minimum. Okay, what about one like this? Let's go ahead and do the derivative first, and then we'll build our table after this time. Let's go ahead and calculate the derivative and get that out of the way. So here's our function. So f prime of x, then, by the power rule, I'm going to get, oh, that's going to be terrible. Why did I pick this one? That was dumb. My derivative is going to look like 11/13 times 24, so I'm going to get 264/13 x to the -2/13 plus 264. Oh, that worked out well, didn't it? 264/13 times x to the 11/13. Okay, thumbs up, thumbs down. Does that make sense? We good? Give me thumbs up, thumbs down, thumbs sideways. Okay. So there's our first derivative. Let's write that. Let's do a couple things with this. Let's go ahead and let's factor out the GCF, which is going to be the least common power of our base, right? We have a common base here of x. I could factor out, I've got powers of x to the negative 2/13 and 11/13. I can only factor out the least power. I could factor out my coefficient though, right? That's the same. So I could pull out a 264/13 times x to the minus 2/13. And then what am I leaving behind? Well, I'm dividing away the entire fraction, and I'm dividing away the entire power of x in the first one. So I'm just going to get a 1. And then here I'm dividing away the fraction. I'm going to end up with x. When I divide away x to the negative 2/13, I'm going to get x to the 11/13 minus negative 2/13. Well, that's just x to the 13/13, x to the 1. Right? And this should sound familiar. We did a bunch of stuff like this, a few weeks ago, right? When we were practicing our power rule and quotient rule stuff, and I made you do a bunch of these with rational exponents for this reason, because we see lots of these. And then if I rewrite this now as one big fraction, I'm going to get on the top 264 times the quantity 1 minus x divided by 13 x to the 2/13. So there's my f prime. You're starting to see now why it's so useful to keep these derivatives in factored form, because when we want to find the zeros, it's convenient to have them factored, right? So where is this? Let's find our critical numbers. Where is this going to equal 0? So f prime equals 0 when the top is 0. Well, show me fingers here. At what x values, there's only one of them in this case, where does the derivative function equal 0? At x equals, good, just 1, isn't it, right? The top is 0 when this factor is 0. So we get one critical number where the derivative equals 0. At what x value is our function undefined? A rational function, meaning a fractional function, is equal to 0 when the top is 0, and it's undefined when the bottom is 0, right? So sign me here, at what value of x is the bottom 0? 0. There you go. Good. So it's undefined at x equals 0. So now we can build our table. So we're on the interval, where was this? From negative 2 to 1. And we had critical numbers at 1. Well, we don't really care about 1 because 1 is already an endpoint, so we're going to be checking that value anyway. We don't really need to include that, but I will, just to show you how the table works. At x equals 1, the first derivative equaled 0. So technically, that is a critical number. It's just not an interior critical number. It was undefined at x equals 0, which is an interior critical number. So over here at 0, we had an undefined first derivative, so that's also a critical number. Now all we have to do is evaluate the function at those 3 candidates and see who the winner is, who the winner for the absolute max and the absolute min are. If we plug, and I'm going to use Desmos on this, because I really don't want to think about all these bizarre fractional exponents. Okay, so our function this time, 24x to the 11/13 plus 11x to the 24/13. And we wanted to calculate, what were our values here for f? We wanted to calculate at -2, 0, and 1. So f of -2 is roughly -3 point, let's call it -3.6. Okay, so there's one ordered pair. At 0, well, we can probably calculate that one without Desmos, right? At 0, we're just going to get 0, right? Hold on. No, we're not. At 0, okay, what's going on at 0 here? Well, actually, hang on here. Yeah, no, never mind. Never mind. We can do that one. Yeah, I was thinking about something else. So if we evaluate this function at 0, we get 0, don't we? Because 0 to any power is 0, right? Anybody see that? Okay, if those were negative powers like we have in our derivative, that's a problem, but they're not. They're positive exponents, so we're okay there. And then the other possibility is at 1. Well, at 1 to any, what am I going to get if I plug 1 in for my answer? What's 1 to the 11/13ths? 1. Yeah. What's 1 to the 24/13ths? 1. So we should get 24 plus 11. We should get 35, shouldn't we? What do you know? 35. Okay. So we got winners. Our left endpoint is our absolute minimum, and our right endpoint in this case is our absolute maximum. Okay, give me 1 to 5. Okay, all right, we're getting the hang of this. There's no point in trying to, we're getting close enough to the end here that I'm not going to try to put in any other new concepts. Maybe let's do one trig function. That's a good idea. Okay, so we've got f of x equals 8 cotangent x. Here's our closed interval that we're considering. So the derivative of cotangent x is what? I'll read lips. Just say it carefully. I can read lips here. Somebody say it carefully into the camera. Isaac said negative cosecant squared x. Okay, so we end up with -8 cosecant squared x, okay, which is the same thing. Whenever you're dealing with cosecants and cotangents and all that stuff, it's pretty useful to just think about these in terms of sine and cosine, right? So this is going to give us -8 over cosecant is the reciprocal of sine, so I'm going to get a sine squared x on the bottom. Okay, so there's our derivative function. Let's consider this then. So is this derivative function equal to 0 anywhere? Yes, thumbs up, no, thumbs down. I'm seeing a thumbs up, or a thumbs down, seeing lots of thumbs down. Okay, nowhere, right? Because the denominator -8 is non-zero always. Okay. Okay, what about, however, where it's undefined? F prime is undefined any place where the denominator is equal to 0. Well, isn't sine squared equal to 0 when sine equals 0, right? Everybody agree? The denominator is going to equal 0 when sine equals 0. Well, we got to look on the unit circle to see where that happens, right? The unit circle, sine is equal to 0 at two places, right? Sine is equal to 0 there and there, because sine is the y-coordinate of the sine of an angle is the y-coordinate of the corresponding point on the unit circle, right? Or hold it. I got that backwards, didn't I? That doesn't make sense. Sine is equal to 0 there and there, isn't it? That's where the y-coordinates are equal to 0. Okay? So that would be at 0, pi, 2 pi, 3 pi, 4 pi, or 0, negative pi, negative 2 pi. Just integer multiples of pi, right? On our interval between negative 5, 6 x and negative 5, 6 pi and negative pi 6, are there any places? So let's kind of look at that span on our unit circle. Oh, darn it. Okay, we'll pick this up next time. See ya. Oh, in my mind, I can hear you all cheerfully saying goodbye to me. That's nice.